review of electrodynamics. You have done it in your BSc and MSc. Probably you followed the books by Griffiths, and at a higher level maybe Jackson and some other books. I will be following these plus some more books, and emphasis will be on problem solving. So, let us begin by stating what electrodynamics is a study of. It is a study of electromagnetic phenomena which is based on Maxwell's equations. And there are four of these. One, which is known as Gauss's law, which says that the divergence of the electric field is charge density divided by epsilon 0. The second one talks about curl of E, and it tells you that curl of E is equal to minus dB by dt, which is Faraday's law. The third law, which talks about the divergence of magnetic field, which it says is 0, that means there are no magnetic monopoles. And the fourth equation, which is Ampere's law, modified by Maxwell later, which talks about divergence of B, which is mu 0, the current density, plus mu 0 epsilon 0 dE dt. Ampere's law initially contained this portion only, and this was introduced, the second term was introduced by Maxwell as known as displacement. Current, which is equal to epsilon 0 dE by dt. These equations are written in vacuum. Medium is not introduced. So, these are the equations which are in vacuum. Equations in vacuum. And for medium, in a medium, these get slightly modified, and the study that you have done in BSc, MSc, you talked about polarizable medium. So, in this course, we will begin with each equation, solve them independently, and then combine them to study the entire electromagnetic phenomena. So, to start with, we have Gauss's law, which says that divergence of electric field is equal to rho over epsilon 0, and this is a result of Coulomb's law. That says that the force between two charges is equal to 1 over 4 pi epsilon 0. Two charges are q1, q2 over r square. So, this Gauss's law is a direct result of 1 over r square behavior of the force law, or we introduce the electric field due to a charge q, which is 1 over 4 pi epsilon 0. This is at vector r q. Let me write it as capital Q. So, this is what I am talking about, q over r square r unit vector, where charge q is at the origin. Let me make a picture to show it clearly. So, if I have a coordinate system with the origin here, and I have this charge q, point charge q sitting at the origin, then at a vector r, which is at a distance r magnitude from the origin, the electric field, let me make it by a different color, points away from the charge for a positive charge, it is towards the charge for a negative charge, and it is given by that formula that we wrote, that this E is 1 over 4 pi epsilon 0. This constant is introduced for convenience and in IS units in the direction of r. So, this is the electric field, and as I said, this directly leads to Gauss's law, which says that the divergence of E is rho over epsilon 0. This is in vacuum. Now, this is due to a point charge. Notice that electric field depends on q linearly, and when there is a linear dependence, there is something called the principle of superposition that follows. And what is principle of superposition? It says that E due to several charges, let me write it q1, q2 and so on up to qn, is going to be sum of charges due to each charge, I equals 1 through n. So, this is going to be equal to 1 over 4 pi epsilon 0, right, q1 over r1 square r1 plus q2 over r2 square r2 and so on. Okay, so, we are assuming these charges are at different points, vectors are different, but again for convenience, for clarity, let me show it on a picture. So, what I am going to do is what the principle of superposition says is that if I have several charges, okay, I am not necessarily sitting at the center, let us say q1 here, q2 at some other point, q3 at some other point and so on. Then, if I want to calculate the electric field at a certain point, let us say this is at a distance r from the origin, and different charges are, let us say this is at r1, this is at r2 and third one is at r3. Then the electric field at this point r due to these three charges will be sum of electric field due to q1 plus sum of electric field due to q2 plus sum of plus electric field due to Q3, right? And this I can write as, now I am going to just take a jump and write this as 1 over 4 pi epsilon 0. E due to Q1 I can write as Q1 divided by R minus R1 square and unit vector in R minus R1 direction. So, that will be R minus R1 distance plus 1 over 4 pi epsilon 0 Q2 over R minus R2 square R minus R2 divided by R minus R2 and so on. So, I can write this as equal to summation I 1 over 4 pi epsilon 0 Q I over R minus R I cubed R minus R I. This is the principle of superposition. So, let us write it again. This is principle of superposition. And in all these things, it is really fun to see what if the electric field depended on charge quadratically. Let us say, what would happen if E, let us say, was proportional to Q square. The question is, will the principle of superposition still be true? I will leave this question for you to explore. As I said earlier, this principle of superposition comes basically because E depends on Q linearly. So, now I can make use of this principle of superposition and say that if I have a distribution of charge, right. So, let us now consider a distribution of charge, and the way we give this distribution is specify by a charge density rho r, okay, or a surface charge density sigma r, then the field would be sum of fields produced by small charges contained in a small volume or a small surface. So, let me show this to you. So, suppose I have some area where charge density is rho r. Then if I take a small volume here, then small charge dq in this will be rho r times dv, where dv is the volume. Or if I have a surface and I take a small area in this, then the charge dq in this area would be sigma r. Let me denote area by capital S, ds. So, what will happen now is that the electric field at any point r will be given as sum of fields due to these elemental charges dq. So, let me quickly write this. I have this volume where there is rho r inside and sigma r on the surface, and I have this coordinate system, and I want to find the electric field at a point r. So, what will I do? I will take a point inside at vector r prime and then calculate the field due to an elemental charge here at this point r. Similarly, I will take a point r prime on the surface and calculate the field. The net expression therefore would be E equal to 1 over 4 pi epsilon 0. I take rho r prime dV prime at that point divided by r minus r prime cubed vector r minus r prime plus 1 over 4 pi epsilon 0 integration sigma r prime ds prime over r minus r prime cubed r minus r prime. That is the formula for the electric field. I have used the principle of superposition. So, I took a small volume here, calculated the field due to that. I took a small surface element here, calculated the field due to that, and summed it up by taking an integral. That is the brute force way of calculating electric field at any point, and we will see we will develop techniques that avoids calculating these integrals most of the time. So, this is how we are going to calculate the electric field. To give you some practice, in the next part of the lecture, I am going to calculate fields due to some simple spherical and cylindrical charge distributions. So, let me just conclude this part. There are 4 Maxwell's equations. Here we focused on Gauss's law, which is divergence of E is rho over epsilon 0, which is based on the empirical Coulomb's law E at r due to a point charge is given as q over r square r unit vector. This is q at the origin, and electric field follows E follows principle of superposition, because of which for a charge distribution given by rho r and sigma r gives field E equals 1 over 4 pi epsilon 0 integral rho r prime dV prime over r minus r prime cubed r minus r prime plus 1 over 4 pi epsilon 0 sigma r prime dV prime over r minus r prime cubed r minus r prime. Sorry, this will not be dV prime, it will be ds prime. So, in the next part of the lecture, I am going to now apply this to calculate electric field due to some simple spherical and cylindrical charge distributions, and for that I will introduce first the spherical and cylindrical coordinates in the next part of the lecture.